In Chapter 4, we've been learning about exponential and logarithmic functions. In Section 4.4, we will now look at exponential and logarithmic equations. Part 1 of Section 4.4, we will look at just exponential equations. Then in Part 2, we will look at logarithmic equations. Exponential equations will be equations with a variable and an exponent in some form. So we can have generic examples. Here our base is 2, but we have this algebraic expression 4x in the exponent part of the expression, and that is equal to 5. Here we have a base of 7, but the variable x is in the exponent, that equals 87. And then here we have an exponential equation involving our natural base e, 5e to the 0.9x equals 15. And again, you can see the variable term is up there in the exponent. When solving exponential equations, there are two basic approaches to solve them, depending on the equation that you have. The first approach is to express each side as a power of the same base, and this can be a simpler form of equation to solve. However, not all equations will be able to be solved using this approach, so then the second approach we will look at is to use logarithms to solve our exponential equations. Let's look at the first solution approach, where we express each side as the power of the same base. When we solve exponential equations by expressing each side as the power of the same base, it can be a simpler form of equation to solve. And you will see this in your textbook, but essentially, if we have some expression with the base b to some expression capital M, and that will equal the same base b on the other side of the equation with some expression capital N, because the bases are the same, then we can just set the exponential expressions equal to each other. So m will equal n. Example 1 on page 504 of your textbook will have two parts. In part A, they give us this equation, 2 to the 3x minus 8 power equals 16. Now, notice here that 16 we can express as 2 to the 4th power. So we can then rewrite this expression in this form. And now, this form will match our definition precisely. The base 2 is the same on each side. And now, we can set our expression capital M, which is 3x minus 8, equal to our expression capital N, which is 4. And then we really have a very basic linear equation to solve. I'll add 8 to each side. 3x equals 12, divide by 3, and therefore x equals 4, or in solution set notation, it'll be written like that. In part B, we're given 27 to the x plus 3 power equals 9 to the x minus 1 power. Now, we do want to rewrite this equation with the same base on each side, and that base will be 3. But in an example like this, you need to be very careful on how you write the exponential expressions that you'll eventually use to solve the equation. So just remember, 27 is 3 cubed, and then that will be multiplied by that expression x plus 3. And then 9, I can write as 3 squared, and that will be times x minus 1. Now, we need to rewrite this expression with the base 3. Remember, this exponent of 3 and 2 is really going to multiply by this expression. So the correct way to set up the problem is going to look like this. This will be 3 to the 3rd power times x plus 3. So it's important you add those parentheses or grouping symbols so you can solve the problem correctly. Now we've expressed each side to the same base, and now we can set our exponential expressions m, which is 3 times x plus 3, equal to n, which is 2 times x minus 1. So we will set those expressions equal to each other. We'll distribute across the parentheses. We'll get 3x plus 9 is equal to 2x minus 2. And then we'll subtract 2x and subtract 9. Eventually, our solution is going to be x equals minus 2 minus 9, which is minus 11. Or again, in solution set notation, it'll be written in that form. Now, do pencil problems 1A and 1B. While some exponential equations can be solved expressing each side as a power to the same base, most exponential equations cannot be solved using that method. And so now we'll look at our other method for solving exponential equations, and that will be using logarithms. Our procedure will be we'll isolate the exponential expression containing the variable, and then we're going to take the logarithm of each side. Now, there are two cases of this step. If you happen to be dealing with an equation that has base 10, you will use the common log. However, any other base, and this is more typical, any other base, you will take the natural log of each side. So, more often than not, this is the step you'll take in solving your exponential equation. And then, once you've done that, we will simplify and solve for the variable. When solving exponential equations using logarithms, pay close attention to the solution set that is asked for in any of your problems. And language is very important. Very often, problems will have the language that requires an exact solution that will be in terms of natural logarithms. The problem then can ask for a decimal approximation or solution, and be sure to follow any instructions on the specified place value to round your answer. So again, you can get an exact solution, which will be some expression that will likely have natural log values in it, and then you can calculate a decimal approximation of that solution if requested. Example 2 on page 505 of your textbook will have us solve two exponential equations. In part A, we're given this equation, 4 to the x power equals 15. Now, if this value had been 16, we could have rewritten it as 4 squared and set x equal to 2 and solved it very quickly. But we can't use that technique. So now what we need to do is take the natural logarithm of each side, because the base is 4, not base 10. So I'll take the natural log of the left-hand side for the x, and then the natural log of the right-hand side will be natural log of 15. Now, how do we solve for the variable x? Well, now we're going to use the power rule we learned in section 4.3. Remember, the power rule allows us to move this variable x out front as a multiplier. So now our equation will look like this. X, natural log of 4, equals natural log of 15. And now this natural log of 4 is a numerical value. It's essentially a variable coefficient. So we will divide each side by natural log of 4. And now we've solved for x. So x will equal natural log of 15 divided by natural log of 4. And this would be what I was referring to as the exact solution in terms of natural logarithms. Now, the text also asks for the decimal approximation, so you can use your calculator and round it to 2 decimal places. X would be approximately 1.95. So notice the two solutions. One is the true exact solution in terms of natural logarithms, and then the other is the decimal approximation. In part B of example 2, we're given this equation, 10 to the x equals 120,000. Now, because this is base 10, this is the one time or one instance that you will take the common log of each side instead of the natural log. So we'll do that. We'll do log of 10 to the x power equals log of 120,000. And again, as we saw in this example, by the power rule, we can move this value of x out front as a multiplier. So initially it'll look like this. X log of 10 equals log of 120,000. Now, we take the common log with base 10 because notice, based on the properties of logarithms and the common log we saw in section 4.2, the log of 10 really evaluates to 1. So this term essentially disappears, and so our final solution is x equals the log of 120,000. So that is the exact solution, and then the decimal approximation will be approximately 5.08. So log of 120,000 is your exact solution. 5.08 is your decimal approximation. In example 3 on 506, we're asked to solve an exponential equation that now will have an exponent with our natural base e. Now, much like you would in other equations, you really want to isolate this term with the variable. So what we'll do is we'll add 3 to each side first. So we'll have 40 e to the 0.6x equals 240. And then we want to divide by this coefficient of 40. And so now we have this simplified equation, e to the 0.6x equals 6. Now, we'll take the natural log of each side. So natural log of e to the 0.6, x equals natural log of 6. Now, remember, by the power rule, that 0.6 is going to come out front as a multiplier. And then here we'll have natural log of e, which equals natural log of 6. Now, just as we saw up in this example, based on the properties of logarithms, not only just with the common log, but now with our natural log, the natural log of e is going to evaluate to 1. So now, this equation will become 0.6x equals natural log of 6. And now to solve for x, we'll just divide by 0.6. So our exact solution will be x equals natural log of 6 divided by 0.6. That decimal approximation will be x equals approximately 2.99. And so again, here's your exact solution and then your decimal approximation. Now do pencil problems 2a and 2b. Example 4 on page 507 asks us to solve this exponential equation. So we have 5 to the x minus 2 power equals 4 to the 2x plus 3. So as we've seen before, we'll need to take the natural log of each side. That will be our first step. So we'll do that. And now, by the power rule, we're going to move these expressions out in front of our natural log expression. Now, this is a more complicated problem. So one thing that's really important is when you apply the power rule, make sure you use parentheses to group those expressions that we move from the exponent form. So we'll have x minus 2 times natural log of 5 equals 2x plus 3 times natural log of 4. And now we need to distribute across these parentheses to eventually solve for x. So once we distribute across those parentheses, we get x natural log of 5 minus 2 natural log of 5 equals 2x natural log of 4 plus 3 natural log of 4. And much like you would do with other equations, you want to group all your variable terms on one side and all the constant terms on the other. So we'll move 2 natural log of 5 to this side, and we'll move 2x natural log of 4 to this side of the equation. Now that we've moved our variable terms to this side of the equation, we're going to factor out x so we can eventually solve for it. So we'll have x times natural log of 5 minus 2 natural log of 4 equals 2 natural log of 5 plus 3 natural log of 4. And now this numerical expression again is really just a variable coefficient. So we'll divide each side by it to eventually solve for x. Our final exact solution will be x equals 2 natural log of 5 plus 3 natural log of 4 divided by natural log of 5 minus 2 natural log of 4, and the decimal approximation would be approximately minus 6.34. This is probably as complicated an example of solving an exponential equation you'll see in our course, but it's still a good review of the technique of using natural logarithms to solve an exponential equation.